Where we will begin is by looking at the wave nature of light, or if you want to use the appropriate scientific term, electromagnetic radiation. So, light or electromagnetic radiation is a type of energy that's embodied in oscillating, orthogonal, electric, and magnetic fields. And in case you haven't heard the word orthogonal before, I don't think it's an extremely common word, or maybe that was just me and I'm explaining it for past me. Orthogonal just means that the two things are mutually perpendicular to each other. And we'll have a picture that we'll look at a little bit later. In a vacuum, these waves move at the speed of light. So we'll use 3 times 10 to the 8th meters per second as a good enough approximation for the calculations that we do. It's really, if you go out an extra decimal place, it's 2.998 times 10 to the 8th meters per second. Before we set up some other things, we should look at the basics of waves, how they are characterized, and what we use that information for. Again, some of this might be familiar from physics, and this is a nice throwback to the chemistry is really just applied physics nature of the subject. So waves, of which I have a picture here, not a terrible picture, but I'm not the greatest artist. Waves are characterized by amplitude and wavelength. And I have these labeled on my wave. So the amplitude is the height of a crest, or it's the depth of a trough. So from my center line up to the top of one of the peaks of the wave, the tops of my waveforms, or the crest, that is on the top side of my line, and then the lowest point is called the trough. And the amplitude is typically, if my wave is just very regular, it's the same for both. And the amplitude is what determines the brightness of light if it's a light wave, or the loudness of a sound if it's a sound wave. The other component is the wavelength, and we use the Greek letter lambda. So that's what this sort of upside down and backwards y is. That's the Greek letter lambda. This is the distance from crest to crest, or trough to trough. You could do it either way. The wavelength determines the energy of the light. And if we're talking about light in the visible spectrum, the energy is related to the color. So wavelength and amplitude are independent of each other, right? If you have light that is green in the visible spectrum, it has a specific wavelength that correlates to an energy. All green light that is exactly the same color has the same wavelength, but you could have bright green light, dim green light of the same color. So the amplitude can vary even while the wavelength stays the same. There's another characteristic of waves called frequency, and it's not listed as the main characterization because we can derive it from the wavelength. Now, this is the Greek letter nu. It kind of looks like a fancy V, but it is not a V. It is a different letter. You may see some places use an F for frequency. They're both representations of the same thing. So the Greek letter nu, frequency, means number of cycles through a point per unit time. So officially our units are cycles per unit time, typically seconds. And we leave the word cycles off. So we'll write it as 1 over seconds, or if you're not interested in typing a fraction, you might write seconds to the -1. Or to make it more hidden but easier to type, you might call it a hertz, after the scientist who dealt with frequency. So we'll abbreviate this as a capital H, lowercase z, and hertz just means 1 over seconds. The way that these are related is through the speed of light. So the frequency times the wavelength, well, I have it written as wavelength times frequency, so let's say it in that order, is equal to the speed of light. And if you check the units on this, you'll see that this works out quite well because wavelength is in meters, Frequency is in 1/seconds, which gives us a speed of light in meters per second. So if you know either the wavelength or the frequency, you can find the other variable by using the constant speed of light. So I have an image here of a bunch of different types of waves. So on the left-hand side, I have waves of different wavelengths. So the distance traveled in 1 second is the constant piece here, and my top wave has the wavelength labeled from crest to crest, so that's wavelength 1, and that, based on our sort of generic setup that we have here, the frequency associated with this top wave is 3 hertz because it goes through 3 cycles in that 1 second distance that we have put up here. The second wave down, you can see that the pieces are closer together. I guess is a better way to put it. Or this wavelength, when you measure from crest to crest, it's definitely shorter. And you can see even in this distance, it's going through more cycles. So when you measure it, the frequency of this wave is 6 cycles per second, or 6 hertz. So a shorter wavelength is a faster frequency or a higher frequency. They're inversely related to each other. And just to take it one more step, our third wave has a much shorter wavelength, right? My distance crest to crest is even shorter, and this has an even higher frequency. It's going through 12 cycles per second, so it has a frequency of 12 hertz. On the right, I have 2 waves with the exact same wavelength. And I've got this marked right. You can see that the crest of every wave lines up with the crest of the next piece in that wave. But what they have are different amplitudes. So the height of each peak in the wave is different. So the top wave has a higher amplitude and the bottom wave has a lower amplitude. I also have kind of a scale here. So this is a really common scale that's shown to give you some perspective of the ways in which we encounter waves in daily life, the applications of those things, and kind of help you get an intuitive grasp for how energy is related to things like wavelength/frequency. So for wavelength, if we start on the right-hand side, a long wavelength is something like AM radio waves. So I would say mostly when we're listening to radio, we're listening to FM radio, which has a really small radius in which you can get that radio station. AM radio is known for being able to reach much longer distances. A weird and interesting part of that is the fact that the wavelengths are so long. So really long wavelengths, AM radio. I don't think there are any bad associations with AM radio. It's a low energy wave. As we start moving to the left, things that we'll encounter, microwave ovens have a slightly shorter wavelength. Now, you wouldn't put yourself in a microwave. But other than being inside one, being outside and exposed to microwaves in general is not considered a bad thing. Now, if you concentrate those, you have the ability to do stuff like heat up your food. But it's not going to completely destroy your food. It's just going to impart some sort of thermal energy onto it. If you keep going, right, these are all shorter or longer wavelengths than visible light. We finally get short enough that we get to visible light. And I mean, we're getting more energetic, and there are energy differences between the colors of light, but no bad associations with light. But we do have an idea of the fact that stuff like ultraviolet light is not good and that X-rays are dangerous, right? We monitor exposure to X-rays and even like all the way up. You've maybe heard of gamma rays. Gamma rays are extremely dangerous. These are much shorter wavelengths, much higher energies, and the higher energy associated with those waves imparts the ability to do things like damage your DNA, cause cell damage, and other things of that nature. All right, it wouldn't be a video without an example problem. So let's practice with some of these calculations. We don't have too many equations so far, which is maybe a good thing. And the first problem is to calculate the wavelength in nanometers of light with a frequency of 4.62 times 10 to the 14 hertz. Our equation relationship, so I have it rearranged here to say that the wavelength is equal to the speed of light over the frequency. You could start with the wavelength times frequency equals speed of light, plug things in, and then do the calculation. Totally up to you. So for my setup, I have 3 times 10 to the 8th meters per second divided by 4.62 times 10 to the 14th, 1 over seconds. And I will get an answer in meters. So 6.49 times 10 to the minus 7th meters. This is what you will always get as your output. And for most of your equations, you will need to input meters for this calculation. But we very often express wavelengths in nanometers, especially things that are in the visible region, because then we can just say 649 if you look ahead to the answer instead of 6.49 times 10 to the minus 7th meters. So you will need to do this unit conversion. I promise you'll get very good at going between meters and nanometers during this module. The next question is to calculate the frequency of a green laser that emits light at 515 nanometers. So now we're looking for frequency, so we need speed of light divided by the wavelength. And my speed of light is still 3 times 10 to the 8th meters per second. But again, we're given a wavelength in nanometers, but I need to put meters into this equation. Now, a quick trick for this, you do not have to use proper scientific notation to put this into the calculation because you are just going to put it into your calculator, right? Which can handle any kind of stuff that you put in as long as you're giving it the correct powers and putting in your parentheses where you need to. So you could just write 515 times 10 to the minus 9th meters. And that's still the same magnitude. It's just not in proper scientific notation. But it doesn't matter because it's just a part of the calculation. And after we plug it in, we'll have our 5.83 times 10 to the 14th inverse seconds or hertz. You could write it as hertz.